Can you see the string?
Yes, sir.
So then today we start doing lanthanide contraction. What do we know? That is, we have seen yesterday across the period, atomic size decrease. Across the period, there is a decrease in atomic size. But for this lanthanide element, or the lanthanide element, we are going to see that this decrease is quite a bit. I mean, the decrease is much more than expected. That's why it is called the lanthanide contraction. And it was expected to decrease, but for lanthanide, it's been seen that the extent of decrease is much more than the expected value. So this phenomenon where you are getting the size of the elements to decrease to a great level, that is called lanthanide contraction. Let's write down the story. That is, as we move along, the lanthanide group মানে cerium lutetium. As we are moving along, lanthanide group from cerium to lutetium, there occurs a gradual decrease in atomic size due to forward screening effect of the A orbital, or you can even write it of the 4F electron. As the number gradually increases, So in the previous class, we have learned that the F electron has a very poor screening effect. In the previous class, when we did about the screening effect and the penetrating effect, there we had learned that F electron has a very poor screening effect. Now for lanthanide, if we see their configuration, we will see that they have F electron. There is the presence of F electron. So that is only being said that, that as you are moving from cerium to lutetium, what is happening? The atomic size is decreasing. Why? This is because due to the poor spinning effect of the 4F electron. And in fact, the more we move from cerium to lutetium, we will be getting that the number of F electron they slowly goes on increasing. And if the number of F electron increases, then this spinning effect becomes more and more poorer. So while the 6s electron that we have, for S orbital, we have the maximum penetrating effect. That also has been done in the previous class. That is what we said. Why? The 4s electron exerts a very poor splitting effect, but the 6s electron they exert a very good penetrating effect. So a combination of this poor screening effect and a very good penetrating effect leads to a decrease in the size of lanthanide. And this phenomenon is known as the lanthanide contraction. Now let's see what happens due to this. It is due to this lanthanide contraction it is due to this lanthanide contraction that as we move, lanthanide contraction is an important topic both for your class 11 as well as in class 12. You will need this thing class 12 also. So read it nicely now so that in 12 there is at least a bit of less pressure in doing one topic. It is due to the lanthanide contraction that as you move from lanthanum to hafnium, the size decreases. Size decreases. And in fact, it decreases to such an extent that the atomic size zirconium and hafnium are almost similar. If you see the periodic table, you see that zirconium is positioned below hafnium. Zirconium and hafnium they are present in the same group. Where hafnium is positioned below zirconium. So going by our normal rule, what should happen is hafnium should be larger in size compared to that of zirconium. The hafnium should be larger in size compared to zirconium. But it is due to this lanthanide contraction, we are seeing that the atomic size decreases greatly. And it is due to this decrease in atomic size, we are getting that zirconium and hafnium has a very similar atomic size. So although it was expected that hafnium should be much larger than zirconium, but it is being observed that due to this lanthanide contraction, the size of zirconium and hafnium is almost similar. So this is an effect of lanthanide contraction. And why does this lanthanide contraction happen? Lanthanide contraction happens due to the very poor screening effect of the 4s electron and the very high penetrating effect of the 6s electron, due to which the size of the element becomes much smaller than its expected value. That's why the lanthanide contraction. Okay, is it clear?
Yes, sir.
Did anyone join the session?
Ayush.
So now let us see the trend in atomic size along different periods. Now we have also seen in the last class that atomic size increases down the group. So that means if we go down the group, that is from top to bottom, what will happen? We will see that the atomic size should gradually increase. So now let us see what happens for the p block element. That is, let's take group 13. So boron, aluminium, gallium, indium, helium. The configurations, let us write down their configuration. So this will be helium, s2, neon, s2, gallium is going to be argon, 4s2, 3d10, 4p1. Indium will be krypton, 5s2, 4t10, 5p1. And thallium is xenon, s2, 5t10, 4f14, 6p1. So this is the electronic configuration. Now, what do we know? That atomic size increases if we go down the group. That means if we move from top to bottom, we are going to see that there will be an increase in the atomic size. If we move from top to bottom, we will be observing that there will be a decrease in atomic size. You know, why is it so? Why is this happening? Let's, and in fact, whether this is only the correct trend observed over here. So normally, our atomic size should have look like this. That is, if this is your suppose atomic size radius. Expected thing is that as you move down the group, atomic size should increase in this. Atomic size should increase in this. But in reality, we are seeing that no, this doesn't happen. In fact, in reality, this is the atomic size of boron. After boron, we get aluminium over here. In boron and aluminium, there's no problem. But for gallium, it is being observed. Boron to aluminium, we see that atomic size increase. For gallium, we are going to see that the atomic size is almost similar. Atomic size of aluminium and gallium is almost similar. Whereas normally it was expected that gallium have a higher atomic size than aluminium. But in reality, it is seen that the atomic size of aluminium and gallium are almost very similar. Then you have indium. For indium, again, we are going to see that atomic size increases. For thallium, we are seeing that the atomic size increases, but the extent of increase is not as much as the expected, slightly. Normally, our expected trend should have been atomic size increases across down the groups. That means if we go from boron to thallium, our atomic size should be increased. But in reality, what we are getting to see is that from boron to aluminium, atomic size increases. From aluminium to gallium, we are getting that the atomic size is practically similar. Although gallium should have been larger than aluminium, we are observing that the atomic size of aluminium and gallium is almost similar. From gallium to indium, this normally increases. Atomic size gradually increases. But again, from indium to thallium, we are seeing that atomic size increases. That is okay. But the extent of increase is not as much as the expected. That means it slightly increases, not so much as it was expected. So now what is the reason behind such observation? So we are mainly getting two exceptional cases. One is aluminium and gallium is having almost a similar size. And another reason is, another exception case is indium and thallium. For thallium, the size does not increase as much as it was expected. So why is it so? What do you think should the reason be? Why both aluminium and gallium has an almost similar size? Why do aluminium and gallium have a similar size? We had to expected that gallium should have been larger than aluminium. But why do we have aluminium and gallium have a similar size? What do you think should the reason be? By the way, how many are doing the class now?
Four, sir.
4.
Okay, you thought the class was from 7:45?
Yes, sir.
No, I changed it now. Forgot. And only for Fridays it is from 7:15. And for other days it is from 7:45. Only on the Fridays it will be 7 from 7:15. and the other days, that is Tuesday, Wednesday, and Sunday, it will be from 7:40. So let's see the reason of why boron, aluminium, and gallium has an almost similar size. So let's write down the reason. So you have to answer this give reason question in your school examination also, because questions from this chapter will come in the form of give reason only. Give reasons will come from this chapter, so you should be well prepared, think out an answer, and write it down. From the electronic configuration, it is evident from this electronic configuration. What do we see on moving from aluminium to gallium? We see the principal quantum number naturally increases 2s2. Here it is 3s2. So that means the principal quantum number E. There occurs, there occurs an increase in principal quantum number. There occurs an increase in principal quantum number. In addition, what does gallium has? Gallium has this 10d electron. And in last class, we have also learned that d electrons also does not have such a good screening effect. D electrons also has a poor screening effect. So this will only be the reason. That is, for gallium, for gallium, there are 10d electrons. 10d electron, which exerts a poor screening effect. Because there is a 10 d electrons in gallium, they exert a poor screening effect because F has the worst screening effect, followed by D. For D also the screening effect is not something good. So it too has a bad screening effect. So that is only written that for gallium, we have this 10d electrons which will exert a poor screening effect, which exerts a poor screening effect, leading to leading to an increase in effective nuclear charge, leading to an increase in effective nuclear charge. Okay. And hence decreases in size. So if you see, we get basically two factors are working over here. That is, from aluminium to gallium, what we observe, we see that the principal quantum number. So on moving from aluminium to gallium, we see one thing, that is the principal quantum number increase. And if the principal quantum number increases, what will happen? Atomic size should increase. If principal quantum number increases, then atomic size should be increasing. But on the other hand, we also have a poor screening effect for this 10d electrons. So we also have a poor screening effect exhibited by the 10d electrons for gallium, and due to that, the effective nuclear charge increases, causing a decrease in the atomic size. So we have two opposing factors. For one factor, that is the increase in principal quantum number, we are seeing that the atomic size is increasing. Another one, for the poor speeding effect of this d electron, we are going to see that the atomic size actually decreases. So due to one factor, atomic size is increasing, and due to another reason, we can say that atomic size should decrease. So now both these two opposing factors are operating simultaneously. Obviously, both the factors are happening together. So that is only what will be written. Now, both these opposing factors are operating simultaneously. Both these factors are operating simultaneously. And in fact, it is observed, in fact, the effect of decontraction slightly predominates. Slightly predominates for the effect of principal quantum number. So this effect of decontraction is the backward spinning effect of the d electron. This is slightly predominant over which effect? That is the effect caused by the increase in principal quantum over the effect of principal quantum number. Thus, it can be said that therefore, radius of gallium, the radius of gallium smaller than the radius of aluminum. So that is why we are getting to see that gallium is slightly smaller in size than aluminium. Although our expectation was that gallium should be larger than the aluminum, but it is due to this effect of decontraction, we are getting to see that the size of gallium is slightly, not very much, rather very slightly. That's why we in fact say that they are similar in size. So it's very slightly smaller than that of aluminum. And in fact, due to the same reason, it is due to the same reason. So for same reason, we have the size of silicon is almost similar to that of the size of germanium. So it is due to the same reason that the size of silicon and germanium are almost similar, and size of phosphorus and arsenic are also almost similar. So you know hopefully that this type of curved lines means that it is an approximately equal to or almost equal. So when I give R of silicon, that means the radius of silicon. Then those curved arrows actually means curved equal to means that it says almost equal or approximately equal. So the radius of silicon is approximately or almost equal to the radius of germanium. Whereas the radius of phosphorus is also almost equal to the radius of arsenic. So this is how we say. That is the meaning of the curly arrows. I hope the explanation is clear to everyone. Is the explanation clear to everyone? Yes or no?
Yes, sir.
Yes, sir.
Yes, sir.
So whatever questions you gave in creating periodic table, for most of the question you will see that your answer will be based on 2 points. Either it will be core spinning effect of F electron or D electron. So either answer to your question will be based on this factor, that is D electrons exert a core spinning effect. Or another way of solving this question will be writing down the electronic configuration. That is, if we write down the electronic configuration, we will get to know the answer. So there are two approaches for mostly solving this sum. One is the poor spinning effect of F electrons or the poor spinning effect of D electrons. Like this way, one particular types of question can come. And another type of question can come where you basically need to write down the electronic configuration. So that is why knowing the previous chapter is so very important. So now let's see the definition of ionization energy. Do you know what ionization energy means? Do you know the definition of ionization energy? So this will be the second periodic property, which is ionization energy. So first, so we need to learn what ionization energy is, what we mean by this term called ionization energy. So let's see the definition. This will be, in short, it is written as IE. So ionization energy, in short, is written as IE, or you can even call it as IP. IP means ionization potential. Same thing, same meaning. So ionization energy or the ionization potential. Ionization energy in short form is written as IE, whereas the ionization potential in short form is written as IP. So let's write down the definition. That is, it is the amount of energy required I is the amount of energy required to remove one valence electron one valence electron from an isolated gaseous species species money you can write in bracket that is it can be atoms also or ions also atoms or ions to the corresponding gaseous cation. Okay. So what do I mean by this definition? Suppose if I want to take out an electron from the last shell. Okay, suppose if you have sodium, what is the configuration? Configuration of sodium? Sodium means 1s2, 2s2, 2p6, 3s1. Suppose I want to take out this last electron. I want to remove this last electron. So now what will the configuration become? Minus electron. That means one electron has been removed. So now it will become Na plus. Cation will be formed Na plus, which will have 1s2, 2s2, 2p6. The last electron has been eliminated out. It has been removed. So what is this ionization energy? It is basically the energy that is required for doing this process. That is the energy required for removing the last electron, money the valence electron. So the energy that is required to remove the valence electron. From where am I removing the valence electron? From an isolated gaseous species. So why do I say a word isolated? Isolated is written so that other gases of atoms, okay, other gases does not interfere with my experiment. So that is why we are taking an isolated system where no one else is present other than sodium. So that is why isolated. If other atoms are also present in the same mixture, then they can cause an interference in my experiment. So that is why we are taking an isolated gaseous atom. That means only that particular gaseous atom, and we are converting it into the corresponding cation. So ionization energy is very simple. That is, if I want to remove the outermost electron, then the amount of energy that I need to supply, that is only called the ionization energy. What is ionization energy? It is the energy required to remove the outermost. From where? From an isolated gaseous species. Why species? Because always it might not be a neutral atom. We can even do it to other ions also. So that is why we are writing a general term, that is isolated gaseous species. So that both atoms and ions are included in my definition. The ionization money Na to Na plus. So H a formation of Na to Na plus. This is known as the ionization. So this process is called ionization. We are converting sodium to Na plus by losing the valence electron. So this process is called the ionization process. And the energy required for eliminating the valence electron, that is called the ionization energy. Is it clear to everyone?
Yes, sir.
Yes, sir.
Ionization means energy required to remove the last electron. If I want to remove the last electron, then the energy that has to be supplied, that is called the ionization energy. Okay, that's it. And on Sunday we are going to discuss mainly how this ionization energy changes across the period and down the period. Basically, in this chapter, this is our motive only to learn about the periodic properties and how they actually vary across the period and down the period. So we are going to see that how ionization energy varies across the period as well as down the group. That will be seen by us in the upcoming classes. And also we'll be taking up exceptions. Obviously, some exceptions will be there. So that will be same, followed by electron affinity and electron negativity. These are the two topics that we still need to do, and we also need to complete the ionization energy. Ionization energy hopefully will be completed in the next class. After that, we can move on to electron affinity and electronegativity. Okay. So then I'm stopping this recording thing.